Well, welcome back. This is Unit 5.4, and in this section, we're going to be talking about the VSEPR theory and hybridization. VSEPR theory. While it's important to understand how valence electrons interact and create bonding, we just went over that by talking about Lewis structures. It's just as important to know about the geometry of the molecule. And this is going to give us insight into how molecules will interact and the mechanisms by which molecules interact with each other. And it gives us information on how fast or slow maybe a reaction is going to happen. This theory is called the VSEPR theory, and VSEPR is actually an acronym that stands for valence, shell, electron, pair, repulsion. So we're talking just about the valence shell electrons, okay, and then pair repulsion. So we know that electrons are negative, and so when they get close to each other, they repel each other. And so it's all these interactions of the valence electrons that give rise to different shapes that molecules have. And there are 5 VSEPR shapes that you're going to need to know for pre-AP chemistry. And these are linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. And we're going to go over each one of these separately. But it pays to know some prefix meanings here. So, for example, we don't have any prefixes here on linear and bent. Linear and bent are the interaction of 2 things bonded to a central atom. So, you know, when we're drawing our Lewis structures, we would have a central atom and then we'd have things connected to it. So linear and bent are when there's 2 things connected to the center. Okay. Tri, right here. So we have 2 cases where we have a prefix tri. Now we know tri means 3. So for these 2, there are going to be 3 things connected to the center. Okay, and then you have 2 different geometric shapes depending on if you have electrons on the center or you don't have electrons on the center. We're going to look at that more close. If you don't have electrons, then this is going to be planar. Planar, okay, from your study of geometry, means flat. So this molecule is going to be able to lay flat if you were to set it down on a table because it doesn't have these electrons on the center. So if you have electrons on the center, then what this is going to do, let's just say we have some bonds here. What these electrons are going to do is interact with the electrons in the bond here, and they're going to repel each other. And this is going to cause it to pop up into a pyramidal shape. Okay, so it's going to bend these down this way. Okay, and this one is really in the back. If you can think about it in the back, it's going to bend it down that way. So it's going to pop up into this pyramid shape, okay, with the distance between these lone pair of molecules and these pretty much being equal. So they're going to push away from each other until this push is equal to these pushes of these other bonds. So it's going to equalize out, come to an equilibrium. But nonetheless, it makes it pop up into a 3D shape. So it's a 3-sided pyramid. Okay. And it all depends on if there's these lone pairs of electrons that are on the center atom. And then tetrahedral. Tetra means 4. So you're going to have your central atom then with 4 things attached to the center. Okay, so these shapes are pretty easy, so let's go ahead and look at each case. Now, in order to do this, we need to make sure that we know how to do nozzle. Okay, so we're going to do nozzle first, because that tells us if we have where our electrons are for our Lewis structure. Okay, and so this should be review because you should know how to do this already. All right, so needed electrons. Carbon needs 8 to have a full valence shell. Oxygen needs 8 to have a full valence shell. There's 2 oxygens here. So that's 16 plus 8 is going to be 24. So we need 24 electrons if all of these atoms are going to have their full octet. But we know that's not true. So we need to get the actual number of electrons. So carbon actually has 4. Okay. Oxygen actually has 6 valence electrons, so there's 2 of them. So that's 12 plus 4 is going to be 16. All right, so now we're going to subtract. So here we're going to get 8. Okay. Now we need to divide that by 2 because we know that it takes 2 electrons to make a bond. So we're trying to find out how many bonds we have here. So in this molecule, we're going to have 4 bonds. So subtract again. So 16 minus 8 is going to be 8. And that tells us our lone pairs, lone pairs. All right, so for the molecular geometry of this, we're going to need 4 bonds and 8 lone pairs of electrons. So we're going to put carbon in the center because carbon always goes in the center. And around that, we have 2 oxygens. So I'm going to draw 2 here like this. We have 4 bonds that we need to distribute. So 1, 2, and go back 3, 4. Okay, now we're going to start checking octets. So carbon, we always start with the central atom. Carbon has 2, 4, 6, 8 electrons around it. So carbon has its full octet. Oxygen has 2, 4. So we're going to have to put lone electrons here. 5, 6, 7, 8. Okay. Oxygen here, 2, 4. So 5, 6, 7, 8. So let's verify we used our 8 electrons. 2, 4, 6, 8. We did. We have our 4 bonds. So this is the geometry for carbon dioxide. Now, we're looking here. Do we have any lone electrons on the center atom that are going to force these bonds downward or away from these electrons? And we don't. We did not have to put any electrons here in the center atom. So these are equidistant. So 180 degrees on this. So this is what we call linear because it can be straight. There are no electrons on the center atom. So this is an example of linear geometry. Now let's look at an example where that's not the case. O3. Okay, so again, we're going to do nozzle. Okay, so 3 oxygens. Each oxygen needs 8 electrons to have an octet. 3 times 8 is 24. Okay, actually, oxygen has 6, so 3 times 6 is 18. So we're going to subtract here. That's going to give us 6. Okay, so we divide that by 2 to get the number of bonds. So we're going to have 3 bonds in this. Okay, subtract again. 18 minus 6 is going to be 12. So we have 12 lone electrons. All right, so oxygen 3. So we're going to put, well, it doesn't really matter. It's not going to make a triangle. So we're just going to put our oxygens like this. 1 oxygen in the middle and 2 on the outside. All right, so we need 3 bonds. So we have 1, 2. So where do we put the third one? So think back. We're going to do a little review here. You could either put it here or here. It doesn't matter. Okay, so let's go ahead and put it here. But what if we put it there? Okay, so remember what this is called? These are both correct. So when these are both correct, this is what we call resonance. This has a resonance structure. Okay, so we need to draw our arrow here to show that both of these are going to exist pretty much at the same time. Okay, so let's concentrate on just this top one here for the distribution of the 12 electrons. So start in the center, 2, 4, 6. Okay, so it needs to see 8, so we're going to have to put a lone pair of electrons here on the center. And if we did this one that way, this one's going to be the same. Okay, so let's go out to this oxygen, 2, 4, 5, 6, 7, 8. Now that has its octet, so do the same over here. 2, 4, 6, 8. So do the same on this one. Okay, now let's verify that we didn't use more than our 12. So we have 2, 4, 6, 8, 10, 12. 12 valence electrons. All right, so here we have our resonance structure for O3. But remember, the one before, we did not have any lone electrons on the center atom, and it was linear. Now on this example, we do have electrons that are on this center atom. So these electrons are going to interact with the bonds here in between these two oxygens. And so they can't lay flat because see, we have this 180 degrees here, but we have 45 degrees here and 45 degrees here. And so it needs to be equal. So these are going to move in this direction until that energy is equaled out. So actually, this is going to look like this. Okay, with this here, this distance being pretty much equal all the way around. Okay, all right, and this, because it can't lay flat, is what we call bent geometry. Because this molecule now bends these two electrons down, bent. Okay, so that's the difference. Are there lone pairs of electrons on the center atom? No, they're not. It's going to be linear. Yes, there is. It's going to be bent. Okay, now that same concept is going to exist when we get over to trigonal. So here we have BH3. Okay, now nozzle. Okay, now boron. The reason I chose BH3 is because I wanted to stress to you and bring this back up again to reactivate your memory. Boron only needs 6 electrons to have a quote octet. Okay, so boron's an exception to the rule. It only wants to have 6 valence electrons. So 6, and then hydrogen, because hydrogen only has that one orbital, that s orbital, in order for that to be filled, it only needs 2 valence electrons. So I wanted to bring this back up so that we could review that, because I know it's been a couple of weeks, so I wanted to make sure I brought that back up for your memory. So 2 times 3 is 6. Boron needs 6, so we need a total here of 12 valence electrons. Boron actually has 3. Hydrogen actually has 1. 1 times 3 is 3. So 3 plus 3 is 6. We actually have 6 here. So subtract those. That's going to give us 6 electrons, but we need to know bonds, so we're going to divide it by 2. So it's going to give us 3 bonds. Okay, subtract again. 6 from 6 is 0, so we have 0 lone electrons. All right, so boron is going to be your central atom because it's the one we have the least of. And then around this, we're going to have our hydrogens. So we're going to equally space them around. So that's going to be in a Y shape. Okay, like this. We have 3 bonds, 1, 2, 3. Okay, and 0 electrons. So let's check. Boron does C6, 2, 4, 6. So that's okay for boron. Hydrogen only needs to see 2 electrons, so 2, 2, and 2. So here we have boron with 3. There's no lone pairs on the center. So this is trigonal. And since there's no lone pairs, then it's flat, planar, because it does, these are equally distanced. So this is going to be trigonal planar. It's going to be able to lay flat. Okay, now let's contrast that with NH3. Now I'm not going to go through nozzle again. I've gone through it 3 times, so that should make the review of that adequate enough for you. So I'm just going to tell you that NH3, we have N in the middle, we're attaching 3 hydrogens. And when you do nozzle, this is what you're going to come up with. We're going to have a lone pair of electrons here that we're going to have to put on the center, because nitrogen 2, 4, 6 needs 8. So we need to put a lone pair there. Now, this lone pair of electrons on the center is going to bend these. So if we're looking at it flat like this on the side, we have these 2 electrons here. We have these 3 hydrogens, and I'm just going to put a small little hydrogen that's going back into the board, or it could be coming out towards you. Okay, because these lone pairs of electrons there, it's going to bend these downward. Okay, and so it's going to pop up into a 3-dimensional shape. Okay, and it's going to be trigonal pyramidal. It's going to be a 3-sided pyramid, trigonal pyramidal, because these lone pairs of electrons are forcing the bonds downward. Okay, forcing all 3 of these bonds downward. All right, and then the final shape that we have here is tetrahedral. Okay, again, I'm not going to go through nozzle, but tetrahedral, we have carbon in the center. Carbon always goes in the center, and we have 4 hydrogens attached to that. Okay, so we're not going to talk about putting a lone pair of electrons here on the center, because at this point, so far, what we've seen in chemistry, that doesn't happen. So tetrahedral, tetra meaning 4 things attached to the center atom. All right, so we have our 5 shapes: linear bent, 2 things attached to the center, linear bent; 3 things attached, trigonal planar or trigonal pyramidal; and then 4 things attached, tetrahedral. Okay, so easy peasy. That should be really simple for you. Okay, so now we're going to talk about hybridization. We're going to use CH4 as our example for this. So let's look at the electron configuration for carbon. All right, so if we look at the electron configuration for carbon, carbon has 6 total electrons. So if we go back to our electron configuration and diagramming, we're going to see here that we have 2 electrons in the s orbital, 1s, and then in the 2s, we're going to have 2 electrons. And then in the p orbital, we're going to take these 2 electrons left over, so we're going to put 1 here and 1 here. Okay, so remember, 2 electrons per orbital. Okay, and before we go up to this p orbital, we need to put 2 electrons here. And then so we have 2 left over, so we're going to put 1 here and 1 here instead of doubling up. Remember, they want to be in their own separate orbitals first before they start doubling up. So if we look at carbon, just the electron configuration for carbon, it would only make sense that since it only has these 2 electrons that don't have a pair here, that when it starts interacting with other atoms, that it only has these 2 electrons to interact. So really, if we think about it in strictly from an electron configuration point, carbon only has these 2 valence electrons that are available to bond, because these 2 electrons are now interacting with each other in this 2s orbital. But we know that's not happening because, remember, CH4 looks like this, where we have 4 hydrogens that are bonded to the carbon. So something must be going on here that allows that to happen. And so this is called hybridization. Okay, so hybrid means a mix of, right? So we're hybridizing some orbitals here. We're mixing up some orbitals. So what Lewis proposed really was that these s and p orbitals hybridize into what's called an sp3 orbital. So we're going to take this electron that's in this s orbital here, and we're going to promote it up to this orbital. But these have different energies, because remember, the p orbital has higher energy than the s. So that's not true. So if we look at going back, these bonds right here between the carbon and the hydrogens, these are all the same energy bonds. Like there's no difference in energy. So what happens is these p orbitals are demoted into a lower energy state. This s orbital is promoted a little bit into a higher energy state, so that we have 4 orbitals here that are the same energy level. And these are called sp3 orbitals. Okay, 1 comes from the s being promoted, and 3 of them come from the p being demoted. Now they're all the same energy level. Each one of these contains 1 electron. So there we have right here these 4 sp3 hybridized orbitals that open up the possibility of hydrogen coming in with its electron to let these 2 share. Here it happens again. Here it happens again. And here it happens again to allow a CH4 to bond. Okay, so if we're looking at carbon, this has an sp3 hybridization. Now, how do we get that? So the way we get it is by counting the bonds around the carbon. So a single bond like this is called a sigma bond. Okay, and we're going to look at different types of bonds. So to get the hybridization, you're going to count the sigma bonds plus the lone pairs of electrons that are around this atom, and that's going to equal what's called a steric number. Steric number, and this just tells us how many bonding locations are around that carbon. Steric number. And so with this, we have 4 sigma bonds. We have no lone pairs, so that's going to be a steric number of 4. So we're going to need all 4 of these hybrid orbitals. So we're going to need all 4 of these to hybridize to give us an sp3 hybridization, 1 from the s and 3 from the p, sp3 hybridization. Okay, so this carbon right here is what's called an sp3 hybridization. Okay. Now, let's go back and look. So on our first example here that we use, CO2, let's get the hybridization here. Well, here we see we have a double bond. Okay, so in a double bond, the first bond that's made here is the sigma bond. But if there's a second or third bond that's available, let me erase that. If there's a second or a third bond available that's made, so if we do NOS for N2, we're going to get this. It's going to be a triple bond. The first bond is always a sigma. Every other bond that's made is called a pi bond. Okay, a pi bond. So this has 1 sigma and 1 pi bond here. This, it has 1 sigma and 2 pi bonds, because both of these are going to be considered pi bonds. So when we're trying to find hybridization, we only count the sigma bonds. Okay, so let me erase this so we aren't confused by that. We're just looking at this. So on this, we're only counting the sigma bonds. So we have 1, 2 sigma bonds, okay, plus how many lone pairs on this carbon? None. There are no lone pairs. 2 plus 0 is equal to 2. So we only need 2 hybridized orbitals. So what's going to happen here is we're going to have 1 from the s and 1 from the p that's going to get hybridized, and the other 2 p orbitals we're going to leave alone. So that's what creates this second bond, that p orbital that we didn't hybridize. So we need 1 s and 1 p. So this is an sp, 2 of those hybridized. So it's an sp hybridized orbital here. So this carbon has sp hybridization. Okay. Now going to this one. So we need sigma bonds. So this first bond here, let me change colors. If we're going to look at the hybridization of this oxygen, we have, oops, it didn't change color. There we go. We have a sigma bond here and a sigma bond here. So that's 2 sigma bonds. How many lone pairs? We have 1 lone pair. Okay. So that's a steric number of 3. So we need 3 hybridized orbitals. So 1 from the S, 2 from the P to hybridize. So that's an sp2 hybridization. sp2 hybridization. 1 from the S, 2 from the P, sp2 hybridization. Okay? Pretty simple. So let's go to trigonal planar. So here we have boron. So 1, 2, 3 sigma bonds. Okay, plus lone pairs. There are no lone pairs on this. Plus 0, so that's going to give a steric number of 3. So we need 1 from the S, 2 from the P. So this is sp2 hybridization for boron. Okay. All right. And then here we have 1, 2, 3 sigma bonds. Plus lone pairs, we have 1 lone pair. So that's going to be 4. So we're going to need 4 hybridized orbitals. So 1 from the S, 3 from the P. So this is sp3 hybridization. sp3 hybridization on the nitrogen there. Okay, and finally, we've already done this sp3. Now, occasionally, you're going to see and you would not be required to know how to do nozzle for this because this is what's called an expanded octet. And I think there's an example of this on your problem sheet. Okay, so xenon tetrafluoride. So this is and it gives you the Lewis structure for this. And it says, what is the hybridization on this? Okay, so again, we're going to count. Let me change my color back. Okay, so again, we're going to count how many sigma bonds. 1, 2, 3, 4 sigma bonds. Okay, how many lone pairs? Well, we have 1 here and 1 here, so that's going to be 2 lone pairs. So that's going to be a steric number of 6. Well, this is where we get into the expanded d orbital octet. So we need 6 hybridized orbitals. So we can only take 1 from S, right? We can only take 3 from P because there's only 3 orbitals in the P to hybridize. So we're going to have 3 of those P. Well, that's only 4, so we need 2 more. So we're going to have to go to that d orbital, and we're going to have to hybridize 2 more orbitals from that d orbital. So this hybridization for xenon is going to be sp3d2. Okay, so that's how you get the hybridization here. And this is very uncommon. Okay, it's not very common that this happens. If I can spell common, very uncommon. Okay, the most common hybridization is sp3. Okay, that's the most common, and this is very uncommon to have to dip into that d orbital to grab out some orbitals to hybridize on that. But I did want to put that on the problem sheet so that I could have an opportunity to explain this. All right, so that's it for VSEPR theory and hybridization. If you need to go back and rewatch this, it's a video, you can do that. Make sure that on my YouTube channel, you give me a big thumbs up, leave a comment if you want to, and make sure you slap that like button right across the face.